Standard old, the thing is set on. Back. Oh, wrong one. There we go. The standard spring dashpot collisional model with a constant coefficient, spring coefficients K, a frictional slider. And the important parts of this is that it has a well-defined coefficient of restitution, and which is constant, which is a way of non-dimensionalizing the dashpot. And it also has a constant binary contact time, which says that any two particles, as long as there are only two particles are involved, will collide for exactly that time. And if the collision time is longer, it means some third party has to be involved. And I'm going to do a quick primer on the notion of elastic granular flows. And I'm talking about regions that are dominated by force chains. The important point of this is that if you take the chain and you compress it a certain degree, the stress you develop is going to be proportional to your intercontact stiffness, K. And in this region, the stresses scale in the form of tau d over K. And if you want to think of that, it's like the induced elastic deformation, how much the particles deform, divided by the diameter. This has two subregimes. The elastic quasi-static regime, which says that the stresses do not change with shear rate. Essentially what happens is you shear the system, forces the particles together into force chains. The force chains rotate and collapse. The rate of formation is therefore proportional to the shear rate. The lifetime is inversely proportional to shear rate. You end up with something shear rate independent. Then there's an elastic inertial regime, which is exactly the same system. What happens is, but when you push the particles together, the deformation not only depends geometrically on how they're compressed, but they have to absorb some of the momentum of the shear. And that for the forces induced reflect the momentum of the shear. So you get stresses that increase linearly with the shear rate, because the extra force is linear with the shear rate over a baseline. Then you also have an inertial regime, which is the famous Bagnold scaling. Also has two subregimes. There is the dense inertial regime, which I used to call the inertial non-collisional regime, which is more accurate, but actually dense inertial just rolls off the tongue easier, which is dominated by clusters of particles. And you have the inertial collisional regime, which is dominated by binary collisions, and that's the old rapid flow or kinetic theory regime. And you get a new parameter, which is K over rho d cubed gamma squared. It's a dimensionless stiffness, non-dimensionalized by the shear rate. And you can interpret that parameter is the amount of deformation of the particle that's induced by the inertial of the system, that is, bang them together, there's going to be some deformation of the particle as a function of the particle diameter to the minus 2 power. Or for this particular talk, the more important interpretation is it's like the binary collision time times the shear rate gamma, which is essentially the ratio of how fast the system is pushing the particles together to how fast they're elastically being pushed apart. Okay, here's an example of those two elastic regimes I showed you, where we plot tau d over k, in this case it's the y coordinate, versus this dimensionless stiffness. And you'll see that there's a region where the stresses do not change with shear rate, or do not change with the dimensionless stiffness. And as you get to very high shear rates, you do see an increase in the stresses that are generated. And we see that in experiments just recently. Here we have measurements of both the normal stress and the shear stress for two different particle types. There's this, and you'll notice that on a log-log plot, the increase has a slope of 1/2. And if you assume that if the stresses are proportional to gamma, then tau has to go like this parameter. This is slightly different because it's for Hertzian properties to the minus 1/2 power, and we'll plot with a slope of minus 1/2 as shown. Here's another old plot, which, again, tau d over k as a function of the stiffness. And you'll see this goes over a variety of solid concentrations from 0.62 to 0.56. And for my book, 0.56 is a moderately dense concentration. You can see that all of them show the 1/2 behavior of elastic inertial at very small values of this parameter, which is very large shear rates. And then some roll off and become elastic quasi-static, and some become inertial. And that leaves you with a flow map, which looks like this. That you can have a region, this is solid concentration versus the elastic parameter. In this region, you get elastic quasi-static behavior, which you'll notice at constant density can only transfer to elastic inertial behavior. And that's because shearing the system does not make the force chains go away. You can only make the momentum appear in the results. But, and this, remember, in this scaling, the shear rate increases in this direction. Down here in the inertial regime, if you force them together fast enough, you can force them together faster than the elasticity pushes them apart, and you can force the formation of force chains, even at relatively small densities, although admittedly it takes an awful fast shearing to get there. And this leads to this rather interesting conclusion that the rapid flow regime is actually out here in the regions of small shear rate on this scale. And what I really want to talk about today is this region here in the inertial non-collisional or the dense inertial regime. And that I thought was the most interesting because it's the regime that's dominated by clusters of particles and in their microscale. And I have a slightly different definition than Christine for a cluster. I would call hers a density instability. Mine's defined as a network of particles that are experiencing long duration contacts through which at any instance one can move between any two particles in the cluster by following a path across interparticle contacts. So all the particles in the cluster are in some way a string of contact points. Oh. Come on. And as a result, that means you can have internal transport of momentum elastically with no collisions. Even though the overall rheology may be inertial. And here's a little picture of our simulation box. You can see it's shearing. This thing down here is a single cluster that appears in the box. However, I've unwrapped it because there are periodic boundaries here. I've unwrapped it to show what it looks like as it crosses the periodic boundary. And you'll see it's a very dynamic structure. And that's because all you have to do is break one bond and suddenly a whole subcluster has flown off the main cluster. And that's just some ways they look. And what we did is we went through and we identified all the clusters in the system. That they're not easy computationally, but you can break them into three broad groups. First one are binary. That's just this one point up here, which means it's collision. Two particles in contact. Then you have simultaneous clusters. Sorry, this is the fraction of all the clusters versus the number of particles in the cluster. You have a large number of what I call finite clusters. And then you have clusters that close on themselves across the periodic boundaries. And that means they're effectively infinite. And those are all the ones involving large numbers of particles out here. So the finite ones typically involve most 30 particles on this scale, and here we have maybe 900 of them. And they're, by the way, in this particular system, there are only 1,000 particles. And a way of seeing what happens is to ask how much of the stress is being supported by clusters of what type. And so here's the fraction of the tau YY stress that's supported by each cluster. Of course, everything adds up to 1. versus this dimensionless stiffness here. And what you see is here, very low values, everything's supported by infinite clusters. Sometimes that breaks down, eventually goes to 0. In the intermediary, there's a region where finite clusters take dominance, and then eventually, as you go down here, it is the collisional interactions that are supporting the majority of the stress. You're worried about effective control volume size. It's amazingly insensitive to control volume size. This goes from 10 by 10 by 10 or 1,000 particles to 25 by 25 by 25, which I think is 15,625 particles. And you'll notice that there's really very little difference. And in fact, there's almost perfect agreement between 20 by 20 by 20 and 25 by 25 by 25 particles. Given time, I'll skip over a few effects and come to the problem. The problem is this one here. If I plot a Bagnall scaled stress as a function of my dimensionless stiffness, elastic fall on a line like this. See, most of them show elastic behavior for some time, for some period. When it's inertial, it's a constant. And the problem with that is, at least the conundrum in my mind, is that if I fix rho, d, and gamma, and the concentration, I fix the stress. Then presumably, I could go in there with my dial-up stiffness matrix and change the stiffness of the particles, go from one end to the other. I go from systems that are dominated by 100% infinite clusters to ones dominated that are 100% collisional, change the entire microstructure, and the stresses don't change at all. So the question becomes, why is the rheology independent of the microstructure? Because that's not what we're told, right? The microstructure is supposed to be important. So that's the first question. Yeah? They're all in contact. No. Oh, that's, well.
Because there are some very weak contacts that you consider.
Oh, yeah. Okay. Very weak contacts are considered.
I consider anyway.
Yeah. Okay. The question is, perhaps there's a little force transmission through the contact. You won't expect if there's an elastic path, then the forces are going to prefer the fast transmission across an elastic path to some slow transmission due to moving particles. And so in other words, what I'm saying here is that before, I assumed that the existence of a cluster meant it was responsible for supporting the stress. Maybe it exists and the stress comes back by some other mechanism. So you might ask, it's really binary collisions what's going on. A particle comes in and collides. Instead of transferring the force through the cluster, it just breaks the cluster apart. What happens? Well, the first method I'm going to show you, which is the second one that occurred to me, is that I actually can compute an equivalent binary collision stress tensor. That is, form a contact between, in the same simulation, I form a contact between two particles, I then compute a stress tensor as if it was a binary collision. Don't worry about what happens until the contact breaks. And the question is, would that be anything close to the actual stresses in the system? And of course the answer is no, until you get to collisional behavior, that you can get that the binary stress can be as low as, and way back here in the infinite cluster system, the binary stress can be as low as 30% of the overall contact stress. Okay, so they do seem to be important. And the other is to took at the Lois et al. Method, where they were forming correlations between particle forces. from which they compute a correlation length. And unfortunately, there's something wrong with that. And this is an example. See, what they did was they used the total force on the particle as a way of computing their correlation. And you'll notice, so here's an imaginary force chain, if you will. Same force on every particle. Every particle's in static equilibrium. Ergo, there's since the total force in each particle is 0, you get 0 correlation and 0 correlation length. So the solution to that is to do basically the same thing, except what you want to do is correlate the forces on the contacts. And that's more or less what I did. And the nice thing here is I have the mechanism for detecting clusters, so I can follow the path only within a given cluster. And here's just some pictures of the correlations within clusters. Here's some infinite clusters, finite clusters, and binary collisions. And here, it's a little funny to call it a cluster. This is a case, so to say, it's a case dominated by binary collisions. But to have any correlation, it has to be a case where there are actually 3 particles in contact in the small times when that occurs. And this is like the correlation lengths within a cluster. And I've done here some things in moderately dense systems from 0.5 to 0.58. This is the correlation length as a function of the dimensionless stiffness. And you'll see that they all go, it's interesting that they all seem to have the same value of about 3.75 until the point that it's exactly the point where they stop being dominated by infinite clusters. They begin to drop off, and they get to a value close to 1 back when you're in the binary systems. I have one example here for a 30% concentration, just to show you how a collisional one would work. And so this demonstrates that indeed forces are transferred along clusters. And as just said, it goes to 3.75 for infinite clusters and near unity for collisional. The other interesting thing is Lois and Al thought that their measurement was related to cluster size. There's obviously no relation here to cluster size at all. Remember, these are infinite clusters, not 3.75 diameter long clusters. I'll skip that due to time, and I'll just say that I've shown by 2 methods that clusters are responsible for internal force transmission. And the sad part of that is there's still no answer to the conundrum I proposed of why the microstructure seems to have no effect on the overall rheology in this particular regime.
Thank you very much, Charles. That's fine. Any questions? Yes.
I think, well, perhaps there is no simple answer to the conundrum, but we in a sense, it's not a new conundrum. We're all familiar with it. We're all, at least the many of us who studied the ideal model of hard sphere in statistical mechanics. This ideal model has no cluster at any time because collisions are ideally instantaneous. So at any time on a picture, you have 0 collision with probability 1. So
yes.
Now this system, and if I compare it to a similar one in which the potentials are soft but nevertheless very stiff, will behave both for equilibrium properties and for non-equilibrium properties like viscosity, will behave very similarly. So there is a continuity of macroscopic or rheological properties between perfectly hard spheres and softer potentials.
I assume you're talking about standard statistical mechanical methods?
Excuse me? I didn't...
I said, I assume you're talking about standard statistical mechanical methods.
Okay, yes.
Okay.
Let's say yes.
Okay, then you've got a lot of implicit assumptions in there, like an entropy, that don't really apply in this case.
Okay, but more generally speaking, it sort of renders familiar to us the idea that perfectly instantaneous collisions on the one hand, and similar systems in which collisions have a finite duration and
My point is
interaction.
these are not similar systems.
May I finish my sentence? Yes, there are similar systems.
No, they're
There
not.
are very stiff potentials. They're strong interactions, very short duration collision, infinitely short in one case, finite duration in the other case, but it's not easy to understand in detail, perhaps, but it's not such a wonder that they behave similarly. Okay.
Okay,
Okay,
that was
got
not
one
a
more
question.
Yeah.
That was a comment.
Do you want to? just a quick one.
I would agree that it's an old conundrum. It was there in the oldest I've seen is in Silbert's paper in 2001. That the rheology doesn't change very much as you change the spring stiffness over orders of magnitude. The one
Well, I
thing-
certainly have shown that not to be true.
It depends. His free surface, that's different.
Sorry?
His one for free surface, that's very different.
Yeah, it may be, but it is in this volume fraction regime. But the one thing that has been proposed is that perhaps even though you have multiple contacts on a single particle, there's only one force that is very large compared to the others. And that is why the binary approximation works. And there is a second transition to a regime where you have forces which are all roughly equal and they sort of hold the particle together. And that is the point at which it breaks down.
Okay, I would have to say I doubt that there's any case where there's one dominant force on the particle, because that would be the first model that I suggested, where it comes in and knocks the particle right out of the cluster. So we would have no force transmission along the cluster, and I've shown that there's force transmission along the cluster. So that one's done with. The second, I'm not quite sure how the whole holding it together, but in a sense that has to happen for a cluster to exist, period. So the system breaks down under your model.
No, they're having quantitative measures of the ratios of forces on a particle. The average force ratio of the largest to the second largest and third largest. And you do see that one is very much larger than the rest on average.
Okay, well in that case it breaks. Then in that case it doesn't really fit, because you would then not have force transmission through the cluster.
Well, I think you've clearly inspired a lot of feeling here, and I think we should go and lubricate it over some coffee, if that's okay.